Hello and welcome to Lecture 2 of A Taste of Quantum Physics, or The Dreams Stuff is Made Of, in Phys 1201. And in this lecture we're going to do exactly the opposite of what we did last lecture. We're going to see how some things that you think of as waves are also particles. Before we get into this lecture, let me just make a disclaimer, and that's that I'm certifiably insane. But if you've been in this course, you probably figured that out a long time ago. Let's just take my training as a physicist as typical. I took, in my undergraduate, way back when dinosaurs walked the Earth, about 8 courses, which were in one way or another about quantum mechanics. And then another 6 as a graduate student, and then considerable amounts of my research are more or less about quantum mechanics, and I would say all of that adds up to just enough for me to have a basic working knowledge of quantum physics. And in this course, we're going to spend one class on quantum physics, which is nuts. But I will say I have a modest goal, and it's that at the end of this, you should understand why this, which is a spectrum of a gas, this is an emission spectrum of hydrogen, why it has lines in it. So last lecture, we briefly reviewed particles and waves and the models of them, and how by 1905 it was clear that these things were particles and these things were waves, but that by the 1920s it started to become clear that you could get electrons to behave as waves, and I haven't shown you the experimental evidence, but there's plenty that you can also make these other things that we think of as particles behave as waves. So this lecture we're going to look at how by 1905 it was beginning to be understood how light can behave as a particle. So I'm going to say that we know that light is a wave. And when I say that, this is a science course, so you should understand that that means we have experimental evidence that light is a wave. The experimental proof that light is a wave is something you've already seen earlier in the course. It's interference. So here's a two-source interference pattern simulated for water, and you can easily observe this in real life with water. And you can see nodal curves where there's almost no wave action, and you can see antinodal curves where there's lots of wave action, and this is characteristic of a two-source interference pattern. Well, you can't quite do it with light like this. You can't shine 2 lasers onto a screen and see an interference pattern for a bunch of technical reasons that we don't have time to get into. But what you can do is take a single laser and shine it through a pair of slits. And then because the light diffracts, the slits act as 2 sources, and you get an interference pattern. And in this simulated one, you can see nodal curves here, and antinodal curves with lots of wave action here. And wherever an antinodal curve meets the screen, you see a bright patch on the screen, because lots of wave action means bright light. Wherever a nodal line meets the screen, you see a dark patch, because hardly any wave action means dark when you're talking about light. And you can see it on the screen. In real life, you don't see any of this because you don't see the light traveling through the air. You only see it when it hits the screen. Well, this is a simulation, but you can walk into a lab and shine a real laser onto the wall through a double slit, and you will see an interference pattern that looks like this with these alternating bright and dark patches because of all the interference. So our evidence that light is a wave is interference patterns, and we already know that interference is a hallmark of waves, so because light interferes, we can say it is a wave. And this was experimentally demonstrated early in the 1800s. So in 1905, it had now been known for about 100 years that light is a wave. Now it's time to see how people figured out that sometimes light doesn't behave like a wave. Sometimes it comes in lumps, like a particle. And this is going to get a little complicated because it has to do with light's interactions with matter. So we start with an electroscope, which you've probably seen in earlier physics courses. It's just a bulb made of metal with 2 what we call leaves, usually made out of gold foil, hanging from it. And when you charge it, then those leaves will repel each other and they stand out, and you can tell that it's charged. And it doesn't matter whether you put a positive or a negative charge on it, those leaves will repel each other. But in particular, it was noticed that a negatively charged electroscope, if you shine UV light on it, will lose its charge. It will discharge. Well, this was first noticed in the early 1800s. At the time, they didn't know about electrons, but later on, electrons were discovered, and it was shown that what's happening is that the UV light is making the electrons literally jump off of the electroscope, and they go zipping away. Well, that's a pretty crude experiment, so eventually people figured out better ways to do the experiment, and here's a typical one. You have a vacuum tube with these two electrodes. You shine UV light in on one electrode. That makes it emit electrons. They travel down the vacuum tube, and when they arrive at the other plate, because the plate they left is now positive, they run around the circuit and get back there, and you measure a current. And so now you can easily observe when electrons are being emitted because you see a current. And the other thing you can now measure is how much current you get for different conditions. And so, for example, higher intensity light was observed to produce a larger current. Now, it might not be completely obvious to you why light should have any effect on electrons in the first place. And we've sort of said earlier in the course that light is an electromagnetic wave, but the meaning of that may not be clear. So here's a cartoon picture of light as an electromagnetic wave, and you have E fields in red and magnetic fields in blue, and you have a wave that consists of the electric and magnetic fields oscillating. As usual, a static picture of a wave doesn't do it much justice. Here's an animation showing the electric fields and magnetic fields oscillating as the wave travels along. So there's the classical picture of light as an electromagnetic wave. Now think about that light hitting a metal surface. And inside that metal, of course, there are lots of electrons, and they're free to move. Well, you know that electric fields are able to accelerate charges like electrons, and so as this electromagnetic wave comes in, it can start making the electrons wiggle around. It does work on them and gets them moving. And once they're moving around and it keeps giving them more and more energy, they can start, ricocheting off other things in the metal, and crazy things can happen up to and including that electrons can be ejected from the metal. Here's an analogy that's going to be useful to us. Suppose we have a swimming pool of water. The water is going to represent the electrons in the metal. And so if you can slosh it so that it goes over the side of the pool, that's like ejecting the electrons from the metal. You and a paddle in your hand are going to represent the UV light. That's what's agitating the water or the electrons to give them the energy to get out. And so in the pool analogy, you just need to give the surface of the water enough energy that you raise it the height h that gets it over the side of the pool. And you can make fairly long wavelength waves. And if you, say, push your paddle harder or use a larger bladed paddle, you can perhaps vary the height of your waves. And this is analogous to changing the intensity or the brightness of your UV light. But you could also wiggle your paddle back and forth really fast to vary the frequency. That's like varying the wavelength and color of the UV light. And so the important point here is that you can make short wavelength tall waves, or short wavelength short waves, not tall, and you can make tall long wavelength waves and small long wavelength waves. So you can vary your intensity and your frequency independently. Now, what matters for getting water out of the pool? You need to provide enough energy to get the water out of the pool. And if you think about this analogy, it should be clear that the intensity is the thing that matters. That's the rate at which energy is delivered, and you need to get energy into the pool to raise it up the appropriate height. Well, the frequency shouldn't matter. In other words, the short wavelength waves will have no easier a time getting out than the long wavelength waves. What matters is the intensity. You have to make the waves tall to get some to splash out onto the edge. And if you've made them tall enough to splash out, if you make them taller, then more should splash out. In other words, if water is spilling out, you increase the intensity and you should make more spill. Well, that we should put a big check mark on, because that's what was observed with the photoelectric effect. If you were observing electrons being emitted, if you increased the intensity of the light, you would get more electrons emitted. Now we come to an observation that just doesn't fit this wave model. It was observed that every metal had a threshold frequency that we'll call F0. And it was different for every metal. And the key thing is that as long as you provided UV light that was of a frequency above the threshold frequency, you would get current flow. In other words, you would have emission of the electrons from the surface of the metal. And that would depend on the intensity, as you would expect. And so no matter how dim the light is, as long as the frequency is greater than the threshold frequency, you'll get some current flowing. But if you provide light that's below the threshold frequency, no current at all flows, no matter how intense you make the light. If you think about it, that's really, really strange. Just think, it's like you're making your short wavelength fairly tall waves, and water is splashing out of the pool. So here's the water splashing out. But now you go to same height of waves, but longer waves, and all of a sudden, even though the tops of the waves are over the side of the pool, no water splashes out. Well, that's pretty strange. But even stranger is it's also as if when you keep your wavelength short, right? You wiggle your paddle back quickly, but with small wiggles, so you get short waves and not very tall. Even though the crests are below the edge of the pool, you still get some water coming out. Well, to resolve this weird dilemma, along comes this guy. And you're probably used to seeing him looking like this, but in 1905, when he was making this proposal, this is what Albert Einstein looked like. Well, he proposed that light could only be emitted or absorbed in discrete packets, I'll call them lumps. Now, it wasn't Einstein's idea. It was first proposed by Max Planck to explain something else. But Planck thought of it as a mathematical trick, not a real piece of physics. But Einstein realized that it would resolve the photoelectric effect. And to understand how, let's go back to our swimming pool analogy. So instead of using a paddle, let's suppose you're splashing water out now by throwing rocks. Well, you can't throw half a rock. You can only throw one rock or two rocks or whatever. But you can throw big rocks and little rocks. Let's suppose you're throwing in big rocks. Each big rock might make a big enough splash that you splash some water out of the pool. If you switch to little rocks, the splashes are too small. And even if you throw in a lot of little rocks, you might be delivering the same amount of energy in as you would with a big rock, but because all those splashes are so small, no water splashes out of the pool. We call these discrete lumps of light photons, and Planck's proposal had been that the energy of a photon depends on its frequency. It's just Planck's constant times the frequency. So notice that that means long wavelength or low frequency light has photons which each carry low energy, whereas high frequency light has a lot of energy per photon. I'm just going to quickly finish up by comparing two light bulbs. So let's say a red light and a violet light with the same power, 40 watts. Remember that means 40 joules per second. So every second each of these bulbs is outputting 40 joules. Well, we can use that to figure out how many photons they each emit, because we know how to calculate the energy of each photon, although I've given it in terms of wavelength, but we can just use the relationship between frequency and wavelength and rewrite our energy of a photon. And so now if you calculate each of these, you see, as you expect, that the violet light with the shorter wavelength or higher frequency has higher energy per photon, and so even though these light bulbs are emitting the same power, the red light bulb is emitting more photons per second than the violet because the violet bulb's photons each pack a bigger punch.